Hi, my name is Dee, and I'm going to present our work on refined deep layer aggregation for multi-disease, multi-view, and multi-center cardiac MR segmentation. We are concerned with the accurate segmentation of cardiac MR images in both short and long axes. Our task is to separately label the blood pool cavities of the right and left ventricles and the left ventricular myocardium. The resulting segmentations serve a wealth of downstream applications, including the quantification of ventricular volume. However, these segmentations also facilitate advanced forms of 3D visualization, such as may be used in image-guided intervention and have research applications within biomechanical modeling. Thanks to the popularity and development of deep learning methodologies, recent years have seen significant progress in attempts to automate this task. The traditional approaches include deformable models and level set methods. However, these classic methods are limited in their robustness for external testing cases. Recently, a variety of learning-based methods have been introduced to this task, including a combination of CNN segmentation with level set refinement. However, such approach is limited in the ability to accurately segment the wide range of anatomy encountered in the clinic. Instead, Qi et al. Sought to inject semi-supervised learning into CNN optimization using dynamic sublabels from the teacher model for unlabeled training data. More recently, a network based on deep layer aggregation has been proposed to merge features from shallow layers to deep layers iteratively, to better fuse information across layers. However, these previously developed deep networks are primarily 2D, because short-axis sequences are acquired with relatively large between-slice distance, which leads to inevitable misalignment between slices due to the gaps as well as to potential threshold inconsistency. And thus the performance of 3D networks is inferior compared to 2D networks. Although 2D methods have achieved good results for the middle region of the ventricles, the apical and basal regions are still challenging, because the apical region is relatively small in the image, and the basal region has unclear boundaries between the ventricles and the atria. In contrast to previous work, rather than relying on the single view information for short and long axis segmentation separately, we are able to leverage cross-view segments to fuse information and adjust minor errors of the delineation in a single view. The results of the proposed method on the MICAI 2021 M&M-2 challenge showed that our method contributes to the improvement of left ventricle, right ventricle, and the myocardium segmentation. I'll now talk through the overall framework of our method. It has a 2D segmentation stage followed by a refinement stage. The short axis and long axis images are segmented independently first, and then are refined jointly to adjust the minor errors, which could be hard to tackle in only a single view. There are 4 networks in total, including 2 segmentation networks in the first stage for short axis and long axis respectively, and 2 refinement networks in the second stage. These networks share the same architecture, except that the refinement networks take more channels as input, including the original image, the corresponding 2D segmentation, and the aligned segmentation from the other view. The backbone of the networks in our framework is a modified deep layer aggregation used in the reference paper, which is able to extract discriminative features from the cardiac MR image slices. Since both the short and long axes are provided and require segmentation, the standard segmentation network is followed by a refinement stage to fuse the complementary features from the other view. We first compute the intersections of the short and the long axis slices based on their world coordinates. For the short axis images, through the intersection lines, we extract segments of the masks from the long axis slice and map them to the short axis image space. Then, we concatenate the short axis image, its corresponding prediction, and the aligned long axis prediction together to form a 7-channel input to train the refinement network for short axis. Similarly, we can align the masks from short axis image spaces into the long axis image spaces and train another refinement network for long axis. In this way, the first-stage prediction results of the cardiac structures can be refined to produce the final predictions. For our experiment, we validated on the MICAI 2021 M&M-2 challenge dataset. 160 training and validation images with ground truths were used to train a modified deep layer aggregation network using a combination of cross-entropy and Diced laws. 40 additional datasets without ground truth delineations were used for online validation. There was also an offline testing set of 160 data for the final ranking. For the pre-processing, we resampled the data to a resolution of 1.25 mm and implemented multiple strategies for data augmentation. Here are some example results of the proposed method. These images are randomly selected from the 32 validation set of one-fold for the short and long axis segmentations. We also present a comparison of the proposed method with different state-of-the-art cardiac MR segmentation methods, including the 2D UNet, a semi-supervised method, and the modified deep layer aggregation. Here we report the results for the online validation set with 40 images used in the public leaderboard. We can see that the proposed method outperforms the other methods in terms of both Dice and the Hausdorff coefficients for the right ventricle segmentation task. Although the modified deep layer aggregation has shown promising performance on the M&M-2 challenge dataset, our proposed refinement method can further improve the accuracy by fusing the complementary information from different views. We also present the performance of the proposed method for the final testing set of 160 data, obtained offline by submitted code and trained models. The first row is the overall results, and the following rows are accuracies per pathology. The results indicate that the generalization of the proposed method is promising even for unseen pathologies. In conclusion, we propose a novel framework to jointly segment the ventricles in both short and long axis images. The method has two stages. Firstly, we segment the two views independently and then refine their segmentations by fusing the complementary information from the other view. The results on the MICAI 2021 M&M-2 dataset showed improvement on the segmentation for both short and long axis cardiac MR images compared to the state-of-the-art segmentation methods. Thank you very much.